Hi, everybody. Today we're going to be going over the review sheet for test number 3. So, in number 1, it says that WY is congruent to XZ. So, what I'm going to do is I'm just going to mark these in the diagram so we can see them a bit clearly. So, here is WY from W to Y, that whole big line segment here. And XZ is right over here from X to Z, that whole big line segment from X to Z. So the question says, which reasons can be used to prove WX is congruent to YZ? So WX is right over here. And notice how WX, this line segment, is a lot shorter than WY. And we need to get information about WX, which is the shorter segment. And notice how YZ is a lot shorter than XZ, which we originally had information about. So when you have information that's too big and you need to end up with information about something that's smaller, that's going to be the subtraction postulate. So if we were to use subtraction here, we'd be starting with one of the long segments. So let's start with WY. And in order to be left with WX, we'd be subtracting off XY, this portion over here, to be left over with WX. We'd also be starting with the other long segment XZ that we originally had information about. And in order to be left over with information about about YZ, we'd also be subtracting off XY. If we take the green segment XZ and we get rid of XY, we are left over with YZ, which we want information about. So remember, in order to use subtraction, we have to be starting with congruent and subtracting congruent. So we're definitely starting with two congruent segments. We're told in the givens that WY and XZ are congruent to each other. We also need to be subtracting two congruent segments. And although it seems obvious that XY and XY are congruent because they're exactly the same, we do need to use the reflexive property to justify that XY is congruent to itself in order to use this subtraction. So the correct answer here is number 2, the reflexive property and subtraction. Numbers 1 and 3 could have been eliminated right away after reading the question and taking a look at what you needed to prove here, because addition postulate is when you are making information bigger, but here we were making information smaller. So I could cross off the addition postulates right away. Moving along to the second one, we're working with coordinate geometry. I know that because it mentions the word coordinates, and it also gives us the coordinates of each of the 3 points of the triangle that we're working with. And the question says, what type of triangle is triangle RST? So we have a bunch of choices here to work with. So let's start one by one. The first choice says to show that we have a right triangle. Remember, right triangles have right angles, and right angles are formed by perpendicular lines. So in order to know if we have a right angle in this triangle, we would have to show that two sides of the triangle are perpendicular to each other. Remember that perpendicular lines have negative reciprocal slopes. So all we need to do to see if we have a right triangle is find the slopes of each of the sides of the triangle and see if any of the slopes are negative reciprocals of each other. So let's do that. Let's find the slope of RS, which is one side of this triangle. Slope formula is subtract the y's divided by subtract the x's. So the y coordinates here are 2 and -3 from points R and S. And the x coordinates are 8 and -2. So that's 8 minus -2. And we get 5/10, which is 1/2. Okay, let's move on and find the slope of, I guess, ST. That's another side of this triangle. So here's slope of ST. So I'm going to be using points S and T. So I'm going to subtract the y values, which are 5 and 2. And I'm going to subtract the x values, which are 4 and 8. And we get 3 over -4. And then finally, we'll find the slope of the last side of this triangle, which would be RT. That's the 2 points that we haven't used yet. So for those 2 points, we have a y-coordinate of 5 and a y-coordinate of -3. And we have x-coordinates 4 and -2. That gives me h over 6, which reduces to 4 over 3. So if you take a look at the slopes, I see that the slope of this side and the slope of this side are negative reciprocals. This one is just this one flipped over with the sign changed. Remember, negative reciprocal means that you flip the fraction and you change the sign. If it's negative, it becomes positive. If it's positive, it should be negative. So we do have negative reciprocal slopes here, meaning that we have perpendicular sides that form a right angle, making this triangle a right triangle. Um, Answer choices 2 and 3 showing that we have an acute angle, all acute angles in the triangle, or showing that we have an obtuse angle in the triangle is kind of hard to do with coordinate geometry because we don't have a formula that we can directly use to show that or the tools to do that right now at this point with what we've learned. So it's pretty easy to say that 2 and 3 were not going to be the right answers here because it's really difficult to show things about angles in coordinate geometry unless they're right angles formed by perpendicular lines. Equiangular in choice number 4 means that all of the angles are equal. So if we have a triangle that has 3 equal angles, that means it also has 3 equal sides because it means it's an equilateral triangle. If it has 3 congruent angles, it also has 3 congruent sides. So if you wanted to show number 4, it's not going to turn out to be the right answer here because we already know 1 is the right answer. We have a right triangle here. But if you wanted to test out 4, what you can do is you can use the distance formula and you can see if all 3 sides of this triangle have the same length using the distance formula. Number 3. So in number 3, it's asking us how the 2 triangles EBC and DCB can be proved congruent. So here's EBC. Let me just highlight it, EBC. And then we also have DCB. There we go, all highlighted. And just because those triangles are on top of each other, they're overlapping, I'm going to draw them separately just so we can see things a bit more clearly. So let me draw the purple one. Okay, so that's E, this is C, and this is B, that's D, that's B, and this is C. So right away, I see that there's an overlap between these 2 triangles. Notice how side BC is a full side of each of the triangles, and it's highlighted in both purple and red. And if we look at the separated triangles, we see that the bottom side of the red triangle is BC, and the bottom side of the purple triangle is also BC, letting us know that they do share that side. It's the same in the 2 triangles. So we can definitely right away know that we have a pair of congruent sides due to the reflexive property. Anything is congruent to itself. They also tell us in the question that AB is congruent to AC. So AB is right over here and AC is right over here. So those are not sides. Uh-oh, can I undo that? There we go. Okay, so AB and BC are not sides of the red and the purple triangle. They are much, much, much longer than the sides of the purple and the red triangle. The sides and the purple triangle sides are much shorter. So before we look at the rest of the information here, I do want to draw your attention to the big triangle here, ABC. since we know it has two equal sides, we know it's isosceles. And you might remember we have two equal sides of a triangle. If we have an isosceles triangle, we also have two equal angles. Just like if we have an equilateral triangle with three equal sides, there are three equal angles. So I know that in triangle ABC, since it has two equal sides, it's also going to have two equal base angles. So this angle is angle DBC, which is right over here in this triangle. And this angle is angle ECB, which is right over here in this triangle. So now we have a pair of angles that we can also use to prove the triangle's congruent. Let's take a look at the next piece of information. So they tell us that BD, which is a side of the red triangle, so it's a side we would definitely be interested in, is 1/3 of the whole side BA. And they also tell us that CE, which is this whole side of the purple triangle here, is 1/3 of the whole segment CA. So let me write this out so it's a bit clearer. So we know that BA and CA are congruent segments. And we know that, oh, that doesn't look like a congruent symbol. And we know that because of our given information. I know it says AB here, but BA is the same thing. I know it says AC here, but CA is the same thing. It's the same two letters. So we're starting out knowing that AB and AC, or BA and CA, whatever you want to call them, are congruent to each other. And we know that if we multiply BA by 1/3, we get BD, which is a side of the red triangle that we're interested in. And we know that if we multiply CA by 1/3, we get a side of the purple triangle, CE, that we're interested in. This is called the multiplication postulate. It's really similar to the addition and subtraction postulates. There's also a division postulate as well, and it works the same way too. With the multiplication postulate, notice how we are starting with two congruent segments. They tell us in our givens that BA and CA are congruent to each other, and we're multiplying each segment by something congruent. 1/3 is the same as 1/3. They're the same number. So BD, which is 1/3 of BA, should be congruent to CE, which is 1/3 of CA. So I'm going to mark that in the diagram. Our conclusion here that BD is congruent to CE. So BD is here, CD is here, and that gives us information about another pair of sides in the So here we have side, angle, side, side, angle, side. So I'm going to pick answer choice 1. Okay, number 4. So we have a bunch of information here, so I'm going to take this step by step. So they tell us that CA is perpendicular to AB, and they already put the right angle here for us. And they tell us that ED is perpendicular to DF, and they already put the right angle in there for us as well. They tell us also that ED is parallel to AB. Before I move forward, I see that I, at this point now, have two parallel lines cut by a transversal. And notice that Z shape. I know it's a backward Z, but notice that Z shape that we have here. Remember that in the corners of the Z, we have alternate interior angles. And we do know that alternate interior angles are congruent when lines are parallel, which they are here. So this is good to go. Okay. We're also told that CE is congruent to BF. So here's CE and here's BF. And they also tell us that AB is congruent, so it's parallel to ED, and it's also congruent to ED. A lot of marks going on here. So already with what we have at this point in the two triangles, I see angle, side, angle, angle, side, angle. So that definitely can be used to prove the two triangles congruent. Unfortunately, it's not a choice here, so get that off. Because remember, the question is which would not be used to prove angles congruent. But that's not a choice here. Okay. Notice how we have information about CE, which is not the whole side. CB is the whole side of this triangle. And we have information about FB, which is not the whole side of this triangle. FE would be the whole side of this triangle. But using the addition postulate, we can take the pieces that we have and make them bigger to get the full sides of each of the triangle. And that would give us another pair of congruent sides that we could use to prove the triangles congruent to each other. So if I wanted to use the addition postulate, I could take the small piece of the side CE, add it with EB, and get the whole side CA. I could also take FB, the piece of the side, add it with EB as well, and get the full side FB. So we do know that we can get the information that CB is congruent to FE. So that gives us another pair of sides to work with. So just to make this a little bit less confusing, I'm going to just redraw it, and I'm just going to put in the conclusions that we drew. Sorry for my horrible, horrible drawings. C, A, B, E, D, F. So our conclusions here, we knew that we had these right angles. That's a pair of angles we can use. We had those alternate interior angles. Okay, my picture is absolutely awful. I'll just put them here, but my picture does not resemble this exactly. I'm a horrible, horrible artist. I thought this would make it clearer, but I think this is just making it a bit more confusing at this point. We know that AB is congruent and parallel to, but congruent to ED. And we just proved or talked about how we can prove that CB is congruent to EF. So let's look through the answer choices. I'll go from the bottom up. So we have HL at the very bottom. So HL is specifically for right triangles, and we do have right triangles here. We also need to have congruent hypotenuses. Remember, the hypotenuses are across from the right angle. And we talked about how with the addition postulate, we could prove that the hypotenuses are congruent to each other. The hypotenuses are here. We also need a pair of congruent legs. We definitely have that with AB and ED, and you can see that in the original diagram as well. These are two legs of the right triangles. So let me eliminate that choice. This can definitely be used to prove the triangle's congruent. Next up is AAS. So I see AAS, AAS. And if you look at the original diagram, you can see it there as well. AAS, AAS. So I'm going to get rid of that one. Okay. How about SAS? So I see SAS, SAS, same in the original, SAS, SAS. So I'm going to get rid of that one. And that leaves us with side, side, side as our answer. And remember, for side, 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 you need 3 pairs of congruent corresponding sides. But if I take a look at sides A, C, and D, F, we don't have any information about them. They don't tell us anything about them in the question, so we can't draw any conclusions about them. So I don't know if they're congruent to each other. Okay. Which statements could be used to prove that triangle ABC and triangle A prime, B prime, C prime are congruent? So let me draw here. So that's A, B, C, and let me draw a second triangle, A prime, B prime, C prime. That's my terrible handwriting here. Okay, so answer choice 1 is telling us that AB is congruent to A prime, B prime. So let me put a mark on those two sides of the two triangles. It's telling us that BC, which is right here, is congruent to B prime, C prime. And it's also telling us that angle A, which is right over here, is congruent to angle A prime. If I take a look at the information we have SSA, SSA, which is the same thing as ASS, ASS. And we know that's not a word that we should be writing on our geometry test. It's not a valid method for proving triangles congruent. So choice number 1 is out. This does not prove the triangle's congruent. So will you remember, I'm going to write here SSA is no good. And if you read it backwards, it's a word that you really don't want to be putting on your geometry test. They're the same thing. Let's check out. So this was 1. So let me do this in black. So I'm going to just reset myself. So 2 triangles again, A, B, C, A prime, B prime, C prime. And I just want to, whenever I make the first triangle, wherever I put the letters, I just want to go in that same order in the second triangle. That's really all that matters. So in number 2, we have AB is congruent to A prime, B prime. We have angle A is congruent to angle A prime. And we have angle C is congruent to angle C prime. AAS, AAS. That definitely is a valid method for proving the 2 triangles congruent. 2 is the correct answer. If you look at choice number 3, there's only information about angles, not about any sides. So that would be AAA. And remember, we talked about why AAA is not a valid method for proving triangles congruent. It doesn't work in every single situation. And if you try out number 4, you'll have the information for SSA again, which is ASS, and that is not a valid method for proving triangles congruent. Which condition does not prove that 2 triangles are congruent? We just talked all about this. SSA, if you read it backwards, it is ASS, which is not a word that you want to be putting on your geometry test. List all the postulates or theorems for proving triangles congruent, so that means the methods, and draw an example for each one. So let me do that real quick. So let me show you guys a picture for SSS. We have 3 pairs of congruent corresponding sides in the 2 triangles. Let me show you guys one for SAS. Let me draw my 2 triangles. These are probably a lot better than mine. I'm going to put in 2 congruent sides, and the angle needs to be in between. Side, angle, side, side, angle, side. Okay, let me move on. Let me do ASA next. So let me make my 2 triangles. So for ASA, I need 2 congruent angles, and the sides in between them need to be congruent. ASA, ASA. And now we'll do AAS. So for AAS, we also, once again, need two congruent angles, but unlike ASA, instead of putting the side in between the angles, we need it after the angles. You could have also put it here. That works just fine as well. AAS, AAS. And our last one is HL. So for HL, we know that we need right triangle. So let me put a right angle in them. And we need congruent hypotenuses and a pair of congruent legs. So you could make this leg congruent to each other, or you can make this leg congruent to each other. It doesn't matter. And there we have HL. Determine whether triangle MNO is congruent to triangle QRS. You don't have to graph the triangles. You can do the question just fine without graphing it. But I'll just pause the video really quick and graph it just so you can see what triangles look like in case that helps anybody see things a bit more clearly. Okay, so I have the triangles graphed here, and the most direct way of proving triangles congruent or not congruent, if that's the case here with coordinate geometry, is through SSS. It's really difficult with coordinate geometry to show things about angles unless they're right angles. So I recommend staying away from it because we don't really have the tools to do that yet at this point with what we've learned in class. So remember, SSS means three pairs of congruent corresponding sides. So if the triangles are congruent, if we find the length of each of the corresponding sides of the two triangles, they should all be the same. So that means that if we do the distance formula 6 times, 3 times for all 3 sides of the purple triangle, and 3 times for all 3 sides of the black triangle, we should get the same measurements for each pair of corresponding sides between the two triangles. If the triangles are not congruent, then as long as we can find one pair of corresponding sides that are not congruent, we've proven that they're not congruent triangles because if they were, all 3 pairs of corresponding sides would be congruent to each other. So let's get started. So from the purple triangle, I'm going to start with MN, which is the first 2 letters. So that is the side of the triangle here. And that should correspond to the first 2 letters from the black triangle, which is QR. So I want to see if MN and QR are congruent to each other, if they have the same length. If they are, then I can move on and test out the other pairs of corresponding sides and see if they also have the same length to show that the triangles are congruent. If they don't have the same length, I'm done because I know already the triangles are not congruent. So I'm going to write one time. So we have x2 minus x1 squared plus y2 minus y1 squared. Let's plug in. So that 1 minus 0 squared plus 4 minus negative 3 squared. Remember that on the radical step, so that's 1 plus 7 squared, which is 49. And this gives us radical 50. You can simplify the radical if you want to. That would simplify the 5 radical too. But you don't have to. You can just leave as is. This should be good enough for our purposes unless we see that we need to simplify it. But this should be good enough for us. Okay, let's also find the length of QR, which we said is the side that's corresponding to MN in the black triangle. So plugging into the distance formula with points Q and R, the x coordinates are 6 and 4, and the y coordinates are 1 and negative 1. So we have 2 squared, which is 4, and we have 2 squared again, which is 4, which gives us radical 8. So notice how these corresponding sides of the two triangles are not congruent to each other. They clearly have different numbers under the radical. They are clearly not the same as each other. Remember that we always end a coordinate proof with a concluding statement summarizing what our calculation showed. So here I can write down triangle MNO is not congruent to triangle QRS because their corresponding sides are not congruent. Okay, so I changed 9 and 10 from the review sheet. So make sure that you make the changes in the question on your own paper. I thought we were going to get to a little bit more than we actually did before the test. But that's okay because we have plenty of time after this test to catch up and fill in those blanks. But I want to focus the review sheet on things that are actually going to be on your test. So please make the changes that you see here to your own review sheet. And that should make things a lot clearer here. So we're given that CA is congruent to CB. So CA and oops, that was a terrible highlighting job here. And CB, okay, I'm leaving it. I'm not fixing it. And we're also told that CD is congruent to CE. And our goal here is to prove that DA is congruent to EB. So we have information about the whole segment AC and the whole segment BC. And we need to get information about DA and EB. So if we have information that is too big, we're going to want to take a part away so that we're left over with the information that we actually need. And that's the subtraction postulate, because we need to make the information that we have smaller to end up with the smaller segments that we need to prove are congruent to each other. So now we have our plan. Let me write up this proof so you can see what this is going to look like. So I'm going to make my 2-column statement reason chart, and sorry for the messy handwriting. I'm going to try to do this as best as possible. So we're told that CA is congruent to CB. Once again, I have awful handwriting, and that's given. And we're told that CD is congruent to CE. That's given as well. So I just wrote it in the same colors that we marked the information in the diagram. So then we said that we're going to have to use the subtraction postulate. So let's talk about what that's going to look like for step number 3. I'm just trying to give myself as much space as possible. Sorry that I'm writing on the diagram. So we're starting off on the side with CA. And from CA, we'll need to take away CD so that we're left over with the part that we want. And maybe it'll help if we just do step number 4 at the same time as step number 3, because CA, take away CD, leaves us over with DA. So if it helps you to do it at the same time, go for it. And that should be congruent to, on the side we have CB, and from CB, we need to take away CE to be left over with EB. And we are left over with EB. So let me fill in my missing reasons here. So the reason here would be the subtraction postulate. Subtraction postulate. And my reason here would be substitution. Remember substitution? Let me fix that up. That looks bad. So remember substitution always follows either the addition or subtraction postulates. And the reason that we're using substitution is because CA minus CD is DA. That's what it leaves us over with. And CB minus CE is EB. That's what the subtraction leaves us over with. So we're just simply replacing the subtraction with what's left over with what the subtraction actually is. And that's what we needed to prove. We needed to prove that DA is congruent to EB. So we just showed that DA and EB are congruent segments. That was a short. So in number 10, we are given right triangles ABC and DEF, where angle C and angle F are right angles. Wow, they already give us all that information, so we don't have to draw any conclusions. It's already here. And they tell us that AC is congruent to DF. And they also are telling us here that CE is congruent to FB. And we need to first prove that triangles ACB and DFE are congruent. And then after we do that, we'll prove that angle A is congruent to angle D. So let me just, so we can see what's going on here. We have the black triangle on the left, and now we have the yellow triangle on the right, just so you guys can clearly see what's going on here. So already we have a pair of congruent sides and a pair of congruent angles in the two triangles. But we only have information about CE and BF. CE is not the whole side of the black triangle. The whole side would be CB. And FE is not the whole side of this yellow triangle. The whole side would be FE. So since we have information about the pieces and we want to get information about the full sides of each of the triangles, we're going to be using addition postulate because we need to take the information about the pieces that we have and make them bigger to get information about the whole sides instead. So when we use addition, in order to get the whole side CB, we're going to be taking CE and we're going to be adding on this piece over here, EB, to get the whole segment CB. And when we use addition for the yellow triangle, we're starting with FB. And we're also going to need to add on BE to get the whole side of the yellow triangle, FE. So recognize when we use the addition postulate to this piece, we're going to be adding this segment. And to this piece, we're also going to be adding this segment. So in our proof, we're going to have to say that this segment is congruent to itself by the reflexive property. We want to use it in the addition postulate because remember, for addition, we have to start with congruent and be adding congruent. Once we use the addition postulate, we will have information about the full side CB of the black triangle and the full side FE of the yellow triangle. That would make the two triangles congruent by SAS, SAS. I want you guys to recognize that this is not HL here. And the reason that it's not HL is because we don't know anything about the hypotenuses here. So let's write up this proof. I don't really have a lot of space here. That's okay. So I just wrote my givens down in my 2-column statement reason chart to save some time in this video over here. So now we have the givens down. So now that we have the givens down, let's continue in the proof and use the addition postulate. Before we use the addition postulate, we do need to make the statement that EB is congruent to itself because we are planning to use that in our addition postulate to add to both CE and BF. So I'm going to write that here, reflexive property. Okay, now let's actually do our addition in the next step of the proof to get the whole sides of the black and yellow triangle. So we're starting, and let's do steps 3 and 4 at the same time, just to speed things up a bit and also to make it a little bit more clear what's going on. Definitely help. So we have CE. That's what we're starting with on the black triangle, and we're adding EB to it. And the reason that we were adding CE and EB is because when we put them together, we end up with the whole side CB of the red triangle. And that should be congruent too. On the yellow triangle, we are starting with FB. And to FB, we're also adding EB. You can also call it BE, same thing. And the reason we're doing that is because FB plus BE gives us the full side of this yellow triangle, FE. Let me fill in my reasons here. So for step 3, that was addition postulate that we were using. And then moving on to step number 4, that would be substitution. Because we are just replacing the addition with what it is. This plus this gives us this. This plus this gives us this. Okay, so now we have enough information to say that the two triangles are congruent, which was part 1 of this proof. So in step number 5, I'm going to say that triangle ACB is congruent to triangle DFE. And we see here that that is by SAS based on the information we have. Side, angle, side, side, angle, side. Okay. And here we have one more thing to prove, and that's to prove that angle A is congruent to angle D. So notice how angle A and angle D are in the same spots of the two triangles. They're both at the top of the two triangle in the same position. So we call those corresponding angles of the two triangles. Remember, once we already know that triangles are congruent, all of their corresponding parts, meaning all of their corresponding sides and all of their corresponding angles, we also know are congruent because the whole triangles themselves are congruent. So we can say that angle A is congruent to angle D because since the two triangles are congruent to each other, all of their corresponding sides and angles are congruent as well. And we can abbreviate this with the letters CPCTC. Corresponding parts of congruent triangles are congruent. Once you know the triangles are congruent, all of their corresponding sides and angles are also congruent as well. And that's it. Remember, a big hint that you have to use CPCTC in a proof is when they tell you to prove that either a side or angles of a triangle are congruent to each other. But your question is not asking you to actually prove the triangle's congruent. I saw that the question is saying prove angle A is congruent to angle D, or it's saying prove side AB is congruent to side DE. I see triangles here. I know that those are corresponding sides or angles of the two triangles. So I know that in order to CBCTC to prove that, I have to first prove the triangle's congruent. Remember, first prove the triangle's congruent, then use CBCTC to make a statement about the sides or the angles. You cannot use CBCTC before you first prove the triangle's congruent. Okay? Triangles Joe and Sam. Okay. Such that E maps up to M. E is congruent to M, I should say. That's what it says here. EJ is congruent to MS. And it's asking us which mapping would not always lead to them being congruent. So let's try out the answer choices. So one says angle J maps onto angle S. Well, that would be ASA, ASA. So that would definitely prove them congruent. So not the right choice. That does prove them congruent. Let me reset. The second choice says angle O, which is right over here, maps onto angle A. That's AAS, AAS. So that definitely does prove the triangle's congruent. 2 is not the right answer either. AAS is definitely a way to prove triangles congruent. So it's not choice number 2. Okay, choice number 3. EO, so that's right over here, maps onto MA. Side, angle, side, side, angle, side. That's definitely a valid method. So that's not the right answer either. So that leaves us with choice number 4. But let's see why choice number 4 is the correct answer. So it says JO maps onto SA. Well, that's side, side, angle, side, side, angle. Or if you go the other direction, ASS, ASS. And we know that this is not a valid method of proving triangles congruent. So that is the correct answer here. Okay, let's move it along. So it says here that we're given that AD bisects BC at E. So AD is doing the bisecting, BC is getting bisected. And we know that a bisector splits a line segment into equal parts. So I know BC is getting split into 2 equal parts, BE and CE. They also tell us that AB is perpendicular to BC, and I know that perpendicular lines form right angles. And they also tell me that DC is perpendicular to BC, and I know that perpendicular lines form right angles. And our goal is to prove that AB, which is a side of this triangle, is congruent to DC, which is a side of this triangle. So I see a big hint here. My question is saying to prove that 2 sides of the triangles are congruent. We don't have any information about these sides. Big hint. First, before we're going to prove the sides congruent, we're going to have to prove the triangles congruent. And once we prove the triangles congruent, then we'll be able to make a statement about AB and CD, which are corresponding sides of the 2 triangles, using CPCTC. But before that, we have to first prove the triangles congruent. So in class the other day, a lot of people were asking me, can we use alternate interior angles here? Yeah, those are alternate interior angles. Problem is, we don't know that lines AB and DC, the lines forming them, are parallel. So if we don't have parallel lines, we don't know that alternate interior angles are congruent to each other. So if parallel lines is not part of your givens, you can't draw the conclusion that alternate interior angles are congruent to each other. So I would not use that because that's not true. They don't have to be congruent if the lines are not parallel. What I would use here are the vertical angles. And now we have ASA, ASA. And from here, after we prove the triangle's congruent by ASA, it's just one more step to prove that AB is congruent to DC by CPCTC. So let's write out this proof. You pause and write the given. So I wrote down my first given, that AD bisects BC at point E. From knowing that, we drew the conclusion that BC was split into 2 equal parts, BE and CE. And we can write as our reason that a bisector cuts a line segment into 2 equal parts. I went ahead and wrote down my next givens. That AB is perpendicular to BC and that DC is perpendicular to BC as well. From knowing that we had perpendicular lines, we drew the conclusions that we had right angles. So for my next step, I am going to write down that angle B and angle C are right angles. And my reason for that is going to be perpendicular lines form right angles. And since I'm using this pair of angles as congruent angles to prove the triangle's congruent by ASA, we do also need to make an additional statement about these two right angles. And we do have to say that the two right angles, B and C, are congruent to each other. And the reason that we can use for that is that all right angles are congruent. If you have any two right angles, they're always going to be congruent to each other. They have the same measure. So all right angles are congruent. From here, we definitely have enough information to make a statement about the two triangles. So I can say triangle ABE is congruent to triangle DCE. And according to our plan, our reason here would be ASA, ASA, ASA. And now that I know the triangles are congruent, it's just one more step to make a statement about corresponding sides AB and CD. I can say that AB is congruent to CD due to CPCTC. That stands for corresponding parts of congruent triangles are congruent. So if we already know the two triangles are congruent, we know that their corresponding sides and angles are congruent as well.